Hello and welcome to this quick review of moles and gas volumes, and the clip should be used in conjunction with your independent study and notes that you've done already. So there's two equations to use when we deal with gas volumes. I'm stating this right at the beginning because the most common mistake people make is to use the wrong one by not checking the data and information that the question gives you. So before we start, we need to do a quick look at ideal gas behaviour. So these gas particles are free to move anywhere on the screen. So those same gas particles are now completely sealed in a container. And they're going to be exhibiting some features if they're going to show ideal gas behaviour. They're all completely spherical. They occupy a very small proportion of the actual volume of the container. All collisions between them are completely elastic with no loss of kinetic energy. And finally, particles move randomly with negligible intermolecular forces between them, especially during collisions. All of these are, of course, approximations that we make in order to use equations to model what is actually happening. So, if you only have moles or volume as your data, in other words, a limited amount of information, you use the equation V equals 24n. So going back to Amedeo Avogadro and his constant 6.02 times 10 to the power 23, he was able to use gas pressures to calculate that 24 decimeter cubed of any gas contains that number of gas particles, 6.02 times 10 to the power 23. Therefore, 1 mole of any gas occupies 24 decimeter cubed, or 24,000 centimeters cubed. So therefore we can say that the volume of any gas is 24n in decimeters cubed, or 24,000 n in centimeters cubed. So a typical exam question might go something like this. It'll ask you to calculate the volume in centimeters cubed, so it specifies which one to use. So it wants the volume in centimeters cubed of hydrogen chloride gas given off when 3.5 grams of NaCl are reacted completely with concentrated H2SO4. So I've put in the balanced equation now. I didn't bother with state symbols because it didn't ask for them. So I'm focusing on my gas volumes and moles at this point. So using moles equals mass over molar mass, I work out that I've got 3.5 over 58.5 equals 0.0598 moles of sodium chloride. Now using the mole ratio from the equation, you can see they're equimolar, so this means a 1-to-1 mole ratio between them. So therefore we can deduce that the number of moles of hydrogen chloride is also 0.0598. So multiplying 24,000 by 0.0598, that gives me 1435.2 centimeters cubed as my final volume for hydrogen chloride gas. Now this isn't the only gas equation that you need to know about at A level. There's another one called the ideal gas equation, which relies a lot more on some of the ideal gas features we talked about a little bit earlier. So the ideal gas equation, or PV equals nRT, is to be used when the question gives you data such as temperature or pressure of the gas. So the first part of the equation, P, stands for pressure in pascals. The V stands for volume in meters cubed. The N obviously is moles of gas. R represents the gas constant, which is 8.314 joules per mole to the -1 per Kelvin to the -1. This is actually found on the data sheet, so you don't have to remember it. And finally we have the temperature in Kelvin. So it's very, very important that you always use these particular units when you use this equation. So when you do exam questions that require the use of PV equals nRT, they will definitely give you some of the data using the wrong units, so expect to have to make some conversions. So the first unit conversion to be aware of is to get from centimeters cubed to meters cubed. So you multiply centimetres cubed by 10 to the power of minus 6. So let me take a moment to explain why it's such a large conversion factor. If you take 1 centimetre as a linear distance and multiply it by 100, you obviously get 1 metre. If we take the conversion factor from 1 centimetre to a metre as 10 to the power of 2, and we multiply that by itself 3 times, you have a cubic metre. If you take the 10 to the 2 section of that calculation, that can be simplified to 10 to the power of 6. So that's how you end up with 1 million centimetres cubed equaling 1 metre cubed. In a similar way, decimetres cubed to metres cubed is times 10 to the power of minus 3. And degrees Celsius to Kelvin is add 273. And finally, to convert from kilopascals to pascals, you multiply times 10 to the power of 3. And I can't stress strongly enough how important it is to learn all of these conversions thoroughly. You will need to be able to do this in an exam without having to think too hard about it, or slow down, or start losing time. If you can do this quickly and fluently and correctly, you will save so much time and get so many marks in PV equals nRT style questions, because they quite often carry at least 3 to 5 marks. So the next thing to do is to look at how to rearrange this equation, because that's the other part of the challenge, isn't it? Not just using the correct units, but deciding how to make what you're looking for the subject. So starting with pressure, volume, moles, and finally temperature. Whichever way round you need to rearrange it, these rearrangements need to be fluent also to get through these types of questions cleanly and effectively. So let's have a look at a typical exam question that would require PV equals nRT. I'll leave the rearrangements on the side for now, but obviously when you're in a test situation or taking an exam on this, you'll need to be able to pull these up pretty quickly and effectively, like I've just said. So I've put the conversions on the left and put in a little reminder of the units. Obviously all of this you would not have in an exam, but I'll leave it here for now to make this one a bit more straightforward. So the fact that they want the relative molecular mass means that you're going to be using moles equals mass over mR, or more importantly, mR equals mass over moles. So therefore we need moles to be the subject of PV equals nRT. So the first thing you do is write out the rearrangement, because doing this shows that you've thought of something and it'll get you a mark. So the next stage is to put in the numbers correctly converted. So I've converted temperature, pressure and volume because all of them were in the wrong or the incorrect format for PV equals nRT. So that gives us 0.002003 moles. So we have the mass, so now we can insert the numbers into our MR calculation, which gives us 159.76 grams per mole to the minus 1. So you can see how in this way a question like this, which would be worth about 5 marks, actually gets you to do quite a lot of work. But provided you lay out your calculations and your workings along the way, you'll pick up marks as you go. Another tip to be aware of is to always use calculator values as you go through a calculation process. Don't round early because it might start to introduce error into your final answer, which might put it outside the range of what the mark scheme is expecting. If they ask for the answer in significant figures, obviously you need to use that. If you don't put the answer in the right number of significant figures, you will lose a mark for that. While we're talking about significant figures, they might ask for an appropriate number of significant figures to be chosen for the answer. This means the least sensitive number of significant figures in the question. So in this question, all of the values are actually quoted to 3 significant figures. So there's no least sensitive in this particular question. So if I was asked to give my answer to an appropriate number of significant figures, I would choose 3 as my appropriate number in this particular case and give 160 because that's the 159.76 quoted to 3 significant figures. Right then, that takes us to the end of this review on moles and gas volumes. Hopefully you found it reasonably useful and have picked up a few tips along the way on what to do with your calculations. So it's a good idea as always to go away and practice a few now to start getting yourself a bit more confident on this. But until next time, thanks a lot and see you soon.